Welcome back, viewers. Now we are going to discuss the lecture number 10 of this course. So in the last lecture we have started with the green functions, and now I want to develop the theory to solve initial loop problem and the boundary loop problem with the help of the green function. So I start with the first one, that is initial value problem. So in this case, suppose I have my second order any differential equation. So that is Lyx is equal to Fx. This is the non-homogeneous equation, and in that case I have the initial condition that y at x naught is some value I am taking. So let us take it as y naught. So this is my y naught, and another initial condition I am taking y dash at x naught. So I call it y dash x. So this is my initial condition, and so this is my corresponding initial value problem, and I want to solve this equation with the help of green functions. So this is my equation number 1. So equation 1 can be splitted into two equations. So we split this one into two type of equation. The first one is L of Yx equal to 0. This is the corresponding homogeneous equation satisfying the initial condition, that is y naught and y dash x naught, and so this is given to me. I can call it as alpha and beta also. And another equation I define as the non-homogeneous equation, that is the equation we have. So this is my L of Yx is equal to Fx, and which is satisfying the homogeneous initial condition with the help of and y dash x naught is equal to 0. So this solving this equation, I get my solution, that will be my ycx, and the solving this equation I will get the solution and I call it ypx. So in that case I know that my solution yx for the equation number 1 will be the linear combination of ycx plus ypx. And if you see this one, then my y at x naught will be yc at x naught plus yp at x naught, and yc is the solution of this corresponding homogeneous. So this will be alpha and plus 0. So this will be alpha, and y dash x naught will be yc dash at x naught plus yp dash at x naught, and this will be again, this will be beta and 0, that will be beta. Okay. So this solution will satisfy. So my yx, the solution I can write, and that solution will satisfy the corresponding initial conditions. So this is my solution of the equation number 1, and this solution is satisfying the corresponding initial conditions given to me. Now, so we start with the general equation. So let's I have a general equation, second order differential equation, Lyx is equal to my Fx, right, and then I have my initial condition y at x naught, I define it alpha, and y dash x naught I define beta. So this is the, and my L in this case I am taking d square y over dx square plus px d by d, sorry, d square over dx square plus px d by dx plus qx. So, this is the same as we have defined the last class. So, this is a linear second order differential operator. So, in this case I will try to find out the Green's functions. So, I will solve the equation Lyx that is equal to 0. So, this equation I solving with the given alpha and y dash x naught is equal to beta. But I know that one thing I also know that L of g x that is also equal to this one, and I know that for x is not equal to xi. So, this equation becomes is equal to 0. So, it means that whatever the Green function I am going to find out. So, this Green function satisfy this condition also. It means whatever the corresponding homogeneous equation I am solving, from where I will get my Green function. So, from here I can say that my Green function will also satisfy the initial condition. G dash means because g is a function of two variable here. So, from here I will say that g x at x naught xi this is equal to beta. So, this is the I can define for my Green function. So, now I want to solve this one. So, I defined my function ycx is equal to c1 y1x plus c2 y2x. So, this one we have defined, and with the help of this y1 and y2x we have found that my c1, that is with the help of variation of parameter also we found that my c1 is minus y2 and this is x divided by dx and my c2x is y1x fx and this one. So, from here, so this is the corresponding c1 and c2 I found, and then I am to write the general solution. So, to write the general solution, I will get my yx of the corresponding equation, I call it equation number 1. So, the general solution of equation number 1 I can write as ycx plus ypx. Okay. So, ycx is c1 y1x plus c2 y2x plus ypx I can write as so c1 is this one. So, c1 is, so from here I can write it will be equal to minus of y2. So, I can call it xi f xi into y1x d xi plus y1 xi f xi w xi y2x d xi. So, this one I can write. So, from here we can write as this is equal to c1 y1 plus c2 y2 plus, and this integral I can write as y1 xi y2x minus y2 xi y1x divided by the Wronskian. So, this one f xi d xi. So, this is my solution. So, that is my solution. So, from here I can define that my general solution is, now I can say that this is C1 y1 plus C2 y2 plus, so this integral, actually if you see that xi belongs to, so in this case my xi, I can say that this xi is, so I can take this integral between x naught to x. So, I can write this as x naught to x, my green function x as I, and this is f xi d xi. So, this is my general solution for the equation number 1. So, from here I can define that my green function will be minus y2 xi when x is less than xi and y1 xi over Wronskian when x is greater than xi. So, this is my green function in that case. To y1x and this will be y2x. So, this is my, so from here my particular solution, I can say that my ypx will be x naught to x f I d xi. So, this is the particular solution I found. Now, from here, what about if I apply my yp at x naught? So, if I apply this one, this integral from x naught to x naught d xi and this value be 0. Also yp dash, so I am taking the derivative with respect to x. So, with the help of the Leibniz theorem, this can be written as from x naught to x. So, this will become del g by del x f I d xi plus putting the value of x here in the stead of xi, put the value of this. So, that will be g x x and it will be equal to f x, and this x naught is a constant. So, it will, so from here I will get this one. So, this can be written as, so from here if I want to apply what will the value of yp dash at x naught. So, this will be again x naught to x naught, that is my g x so this one plus g of x naught and my f of x naught. So, this one I will getting. So, this value is equal to 0, and what about this one? This is also 0, because I know that my x naught is the initial condition and gx is the solution of the corresponding homogeneous equation. So, this is equal to 0, and from here I can say that yp, the whatever the particular solution I am having, that solution satisfying the homogeneous corresponding the homogeneous equation, homogeneous initial condition, that is this is equal to 0 and this is equal to 0. So, we start with the, if you see this one, we have started with the problem this one, and then we split this one into two parts. So, this one we have used to find out the green functions and the corresponding values of C1 and C2, and then with the help of the particular solution we found, we have showed that this satisfies this homogeneous initial condition, and then that is ypx is our particular solution. So, now let us take one example, then the things will be more clear. So, let us take one example, example number 1. I want to solve my equation. So, L yx, I am taking y double dash plus 4y is equal to fx, and that I am choosing just 1. So, basically I am solving, if you see, y double dash plus 4y equal to 1. So, this one we are solving, and I already know that how to solve this one, because in this is a linear second order equation with constant coefficient and the right hand side function is just 1. But I want to solve this one with the help of green functions. So, now first I will solve the equation L of yx is equal to 0. Now, I putting the initial condition also. So, I will define at y pi is equal to 0 and y dash pi is equal to 1. So, this is my initial condition. So, I want to solve this one. So, this is an initial condition, y dash pi is equal to 1. So, I want to solve this one. So, if I solve this one, then from my previous knowledge I know that 4y is equal to 0, and then I can find out my corresponding characteristic equation, that will be m square plus 4 equal to 0, and from here I will get my m is plus minus 2 iota, and from there I can define my solution y1x as cos 2x and y2x as sin 2x. So, from here I can define my linear independent solution, that is cos 2x and sin 2x. So, from here I will get my solution ycx will be cos. So, I want to define this one. So, this one will be C1 cos 2x plus C2 sin 2x. Now, I will try to find out the value of C1 and C2 from here. So, this is my corresponding complementary solution. So, complementary solution I can find out, then from here I can find my, now it is given that yc at pi, that is given to me. So, this will be C1 cos 2 pi plus C2 sin 2 pi, and that value is given equal to 0. So, from here I know that cos 2 pi will be 1. So, it will be C1 plus, and then it will be 0 is equal to 0. From here I can get that C1 is equal to 0. And then I will also define yc dash at x. So, yc dash at equal to x I will define. So, this will be minus C1 2 times sine 2x plus 2 C2 cos 2x, but this value is already 0 because C1 is already 0. So, from here I will get 2 times C2 cos 2x is equal to 1. So, this one so that is derivative, sorry. So, this is the derivative I have, is that is equal to my ycx, because C1 is already 0 from this initial condition, first initial condition. So, from here I can say that my yc at pi will be 2 C2 cos 2 pi, and that is equal to 1. So, from here I can say, and the cos 2 pi is 1. So, from here I can say that my C2 will be 1 by 2. So, from here I am able to find my ycx will be, C1 is 0. So, it will be half sine 2x. So, this is I am able to find. Now, I want to find the corresponding green functions with the help of this one. So, from here I can say that my corresponding green functions. So, now I want to find my ypx. So, ypx will be from pi to x d xi. So, f xi is 1 here in this case. So, it will be pi x d xi, where I know that my green function will be, in this case it will be cos 2 xi into sine 2x minus cos 2x sine 2 xi divided by the Wronskian. So, the Wronskian into d xi. So, from here the Wronskian, I know that the Wronskian in this case will be, so this is my cos 2x and this is sine 2x. So, this will be minus 2 sine 2x and this will be 2 cos 2x, and that will value be equal to 2. So, in this case I will get the Wronskian, that is equal to 2. So, generally we take the positive value if it is coming negative. So, from here I can define my ypx will be from pi to x, and this will be half, so 1 by 2, and this one I can write as sine 2 x minus I d xi. Okay. So, this one I can define from here, and if I solve this one, so this is my ypx. So, this is my ypx. Now, from here I also, so ypx I am able to found. So, this ypx, now I take what will be the value of yp at pi. So, yp at pi, this will be the integral from pi to pi sine 2 x minus I d xi, and this will value equal to 0. Then yp dash x will be again, so in taking the derivative of, so it would be cos 2 x minus I into 2. So, into 2 d xi plus, then we found the green function. So, this will be x x that will be the value, because I am putting this upper limit in the function, and then the function f(x) in this case it is 1. So, from here I just define that what will be the value of yp dash at x equal to pi. So, in this case this integral becomes 0 to cos plus g pi pi, and this is equal to 0, and this will be equal to 0 because g pi pi is the solutions of the corresponding homogeneous equation. From here I can say that my yp at x equal to pi will be 0. So, from here I can say that my ypx Lyp, that my L of yp is equal to fx, that is equal to 1, and it is satisfying the condition, the homogeneous initial condition, that is this equal to 0 and this is again yp dash equal to 0. So, from here I am able to solve this one, and now if I solve the integral value, then my yp will be, so I just want to take the integration of this one. So, from here my ypx will be, in this case it will be 1 by 4. So, if I just ycx is half, so it will be 1 by 4 minus cos 2x by 4. So, then my general solution yx will be 1 by 2 sin 2x plus 1 by 4 minus cos 2x by 4. So, that will be my general solution for the given equation. If I solve the same equation with the way we have solved in the previous lecture, and you can verify also that using the, if I use the operator method, then I can find this equation as d square plus 4 yx is equal to 1, and from here my ypx I can define as 1 over d square plus 4 into 1, and this one I know that we can write as d square plus 4 inverse, and 1, this one I can write as E0x, and from here I can find that putting the value of 0 in instead of d, so it will get 1 over 4. So, my ypx in this case it will be 1 by 4. So, from here I can find my solution, and then, so if I solve this one, my general solution will be, so this general solution in that case will be C1 cos 2x plus C2 sin 2x plus 1 by 4, and then I apply my initial condition. So, my y of pi will be C1 cos 2 pi plus C2 sin 2 pi plus 1 by 4, and this value is given to me is equal to 0. So, from here, so this is 0, this is 1. So, from here I can get my C1 plus 1 by 4 is equal to 0. So, my C1 will be minus 1 by 4. So, this will be minus 1 by 4, and then I will take the derivative of the solution y dash at x. So, this one will get minus 2 c1 sin 2x plus 2 times c2 cos 2x. So, this is my derivative, and then I put value equal to pi. So, in that case it will be minus 2 c1 sin 2 pi plus 2 c2 cos 2 pi, and that value is given to me, that is equal to 1. So, from here I can say, so my C1 is already minus 1 by 4. So, this one I can write as 2 times C2. So, cos 2 pi is 1. So, I can write this as minus 2. So, C1 is, but this value is always 0. So, this is equal to 0. And from here I will get 2 C2, and that is equal to 1. So, from here my C2 is 1 by 2. So, my C1 is minus 1 by 4 and C2 is 1 by 2. So, from here I can write my general solution, that is yx is equal to, from here, so C1 is minus 1 by 4. So, it is minus 1 by 4 cos 2x, C2 is half. So, half sin 2x plus 1 by 4, and from here I can write that it is equal to half sin 2x plus 1 by 4 minus 1 by 4 cos 2x. So, this is the same solution we got for with the help of green function. So, this solution and the solution we have solved using the green function, so this and this, so both are same. So, from here we verify that whether we are solving this equation with the help of the operator method or we are solving the same equation with the green functions, we are getting the same solution. Now, we take the, so this is the initial problem I have taken. Now, let us start with the boundary value problem. So, I take the boundary value problem. So, in the boundary value problem, so let us see that how we are able to find the green functions. So, let us take one example of that boundary value problem. So, let us solve this equation. I want to solve the equation y double dash x is equal to some function f x with the boundary condition so boundary condition I am taking y0 is equal to 0 and y dash 1 is equal to 0. So, this is the boundary condition I am taking. So, this is the mixed boundary condition. It is if we see, this is a Dirichlet type boundary condition and this is the Neumann boundary condition. So, it is a mixed type of, we have a function and its derivative. So, in this case I will solve the green function. So, the same way we will split this one into two parts. First one I will solve like this one, y double dash x equal to 0 with the boundary condition, whatever the boundary condition we have, and then I will solve the whole equation yx is equal to fx with the homogeneous boundary condition. But in this case the boundary conditions are already homogeneous. So, the same boundary condition I am putting for the both the equations. Now, from here, and I also know that the second derivative, it means del square over del x square, this will be equal to the Dirac delta function, okay, and this will be equal to 0 when x is not equal to I. It means that in that case also I can say that 0 will be 0 and gx at 1 at 1 xi, this will be 0 in this case. Now, if I want to solve this one, so solving my y dash is equal to 0, taking the integration one more time. So, I am taking my y dash is equal to some constant c, and from here I will get my yx, I will write as a cx plus d. So, this is my equation of the line. Okay. So, this my yx is equal to cx plus d. So, from here, and now in this case my x, so if you see here my x is lying between 0 and 1, because value is given at this one. So, I can from here I can say that this is my solution of the equation, and x belongs to, I can say it is belonging from 0 to 1. Now, from here I can define my Green's function. So, this Green function will be Cx plus d when x is less than xi, and I can define as, so I can just define as C1 d1 and then C2x plus d2 x is greater than xi. So, this one is the Green function we know I can define from here, and then I can find the value of C1 d1 C2 d2. So, this is I am doing with the help of the properties of the Green functions, and from here I will apply the properties. The first property is I am implying that my function g is continuous at x equal to xi, because you can find out the Green function by solving this homogeneous equation also, and then we put the boundary condition, and then we can find the corresponding coefficients. But here I am applying the another method, that is with the help of the properties of the Green functions. From here I can write that C1 xi plus d1 is equal to C2 xi plus d2. So, from here I can write my C1 minus C2 xi plus d1 minus d2, that is equal to 0. Okay. Now, I also know that these conditions, the bounding condition are satisfied for the given function. So, because in this case I already know that I can, from the another equation, the jump discontinuity, I can find the another equation, and that using those equations we can have a 2 equation and the 4 variable C1, C2, d1, d2 we want to find. So, what I can do is that I can apply this boundary condition for the given function also. So, this is the corresponding Green function. So, from here I can say that g of 0 xi. So, g of 0 xi, because x is less than xi I am taking, and xi is in this case will be lying between 0 and 1. So, I can say that this will be C1 so it will be C1 into 0 plus d1, and that value is given to me. So, from here I can say that d1 is equal to 0. So, from here I am able to eliminate the d1. Now, I also know that g, the del g by del x. So, let us find out this one, that what will be the value of this one. So, I just want to find out this one. So, this value will be equal to so it will be C1, I am taking the derivative with respect to x when x is less than xi, and it will be C2 when x is greater than xi. And from here I am able to find this value. So, from here I can put my del g by del x at 1 xi. So, it means that 1 is, so I am putting x equal to 1 here. So, I am taking this condition that x is greater than xi. So, in this case I can say that my C2, this is given to me and this value is equal to 0. So, from here I can also able to eliminate C2 equal to 0. So, from here I can now write my green function. So, this green function is C1x when x is less than xi and C2 is 0. So, it is D2 when x is greater than xi. So, now we have only two C1 and C2. Now, what I will do, I will take the help of these properties, because just I wanted to use this one. So, with the help of this continuity equation and the jump equation, I can find the value of C1 and D1. So, this part I will do now for this green function, because this is the green function after putting the boundary condition. So, from here first property gives that it is continuous at xi. So, from here I can say that C1 C1 xi into xi is equal to D2. So, this is one of the equation, and from the second property, so that second property is that del g by del x has the jump discontinuity of magnitude 1 about x equal to xi. So, from here I can say that del g by del x minus del g by del x is equal to 1. From here I can say that, so this is my D2, so it will be 0 minus C1 and that is equal to 1. So, from here I can say that my C1 is minus 1. So, once I have C1 is equal to minus 1, from here with the help of this one, so C1 is equal to minus 1, D2 in this case will be minus of xi. So, with the help of this one I am able to find my green function now. So, C1, this is my green function. So, C1 is my, so I can define this function as minus x when x is less than xi, and D2 is minus xi. So, this is minus xi when x is equal to xi. So, this is my green function. So, once I am able to define this green function, now I can find my particular solution ypx. So, ypx will be from 0 to 1 z design. So, this one I want to find. Now, so with the help of this one, ypx is equal to from 0 to 1 gx, this one I am able to find my ypx. So, in this case, because if you see, we have started with the equation with fx is unknown. So, now I define the fx. Let us take a simple one. So, let us take fx equal to x square. So, if I take x square, then my ypx I can define as from 0 to x my gx into x square into xi square d xi plus from x to 1 from x to 1 dz. Why I have done that? Because my the green function is defined for in the piecewise form when x is less than xi, this value and this value. So, from here I can define my so this will be, So, when my xi is lying between 0 to x, it means when my xi is, so from here I can say in this condition my xi is less than x, and in this one my xi is greater than x, because xi is lying between x and 1. So, when xi x is greater than xi, this is value of xi. So, I can put from here 0 to x, and then this will be minus xi into xi square dxi plus x to 1, and this value is minus x. So, it will be minus x xi square dxi. This one can be written as xi square dxi. So, I will just solve this one, 0 to x minus of xi cube dxi minus x to 1. So, this x I can take outside, this will be xi square dxi. Okay. Now, I will solve this one further. So, from here I will get, so it will be xi 4 by 4, applying the conditions here, minus x, and this will be xi cube by x to 1. So, from here I will get 1 by 4. So, it will be x power 4 minus 0 minus x by 3, and this will be 1 minus x cube. So, from here this one I am putting this limit. So, once I get this value, I will get minus x power 4 by 4 minus x by 3 plus x 4 by 3. So, from here if you see, I can write this value x 4 by 3 minus x 4 by 4 minus x by 3, and this one can be written as that my yx will be x power 4 12 minus x by 3. So, this is the solution for the corresponding equation with the help of Green's functions. You can solve this equation, because if you see that I have solved this equation, y double dash is equal to x square with the initial condition that y at 0, with the initial condition that y at 0 is 0 and y dash at 1 is 0. So, you can also solve this equation with the previous method, where we were solving the differential equation with constant coefficients, and the right hand side function is a polynomial, so that is x square. So, if you solve this one with the previous methods, then you should get the same solution as this is. So, this is you can take as a homework to verify whether you are getting the same solution for this one with the operator method or not. So, thanks very much for this lecture. So, in this lecture we have discussed that how we can develop the Green functions for initial problem and the boundary value problem, and then we also solved few examples and verified that if we applying the Green function or the methods were solved with the help of operators, then we found that the both results are coming same. So, in the next lecture we will go further and we will try to find the apply the Green function for some other problems. Thank you very much.